All right, thanks, Lydia. So we often need information on the go. For example, we all just traveled here to Quebec City. Along the way, we needed information, flight confirmation number, hotel reservation numbers, maybe even needed the ACM registration numbers to get discounts for our registration. All of this information is kind of existent in our email, which increasingly serves as an extension of our memory. Now, in this talk, we introduce our system, WearMail, that enables on-the-go access to your information in your email with a privacy-preserving human computation workflow. This work has been done with my colleagues, Fanglin, Chen, Kenneth, Huang, Irene, Rohan, Jadvani, and my mentor, Jeff Bigham at CMU. Also joint work with collaborators Raymond and Walter Lasecki over at Michigan. Now, every day, we look for many information on the go. For example, here's a user who's looking for an address to the place he's going. Or look for items such as building access code when we're entering the building. Or even look for room numbers where the meeting is taking place. In all these cases, oftentimes, the information that we're looking for lies in our email. Email has remained an extension of our memory, and we store large amounts of personal information in our email. We were interested in understanding what kind of specific personal information that people are looking for on the go. So we recruited 200 Mechanical Turk workers and asked them to submit a screenshot of their Gmail search history from their mobile phone. Each participant provided 2 to 4 queries and explained what they were looking for and where they were looking for. After we looked at the data, it turns out there's a long tail of personal information requests that people perform, such as order numbers, such as like Amazon order numbers, eBay order numbers, or even like Best Buy coupons, or coupon codes from Costco, Pizza Hut, URLs such as Craigslist URLs, Twitch gaming URLs, blogs, even event details, contact addresses, and many, many more personal and private information. There were 250 such unique long tail of information queries. And most of them seem to be, most of the people searched for them on the go. Now, the current conversational assistants, however, can handle a relatively few limited set of specific information requests. So A, they're limited by their scope of knowledge, and B, they're not open to direct access from contributors or developers of these systems. So we built WearMail, which is an interactive crowd-powered system that handles myriads of private information requests on the go. So the way it works is, so here we see, for example, a user who's asking what his ACM membership number is on the go. And after that, immediately, crowd workers work on the background and select emails where they think the information might lie. And after that, they feed examples to kind of create programs on the fly that can then extract information, and the results are returned to the user immediately within a few minutes. Now, when designing WearMail, one of the key concerns for us is how can we enable crowd to work with a private and sensitive data like email? Well, obviously, one approach would be like Email Valet, where you could let users select a subset of their emails and give full access to the content of the email to crowd workers. However, we decided to never expose any of the email content to crowd workers and choose to do this in a more privacy-preserving way. First, by using an obfuscated metadata interface, crowd workers could create a filter set or a subset of email where they think the information might lie. Second, we use crowd workers to tell us what type of entity the user is looking for. We then use a conventional named entity recognizer, which, given a text, can tag any kind of categories like date, person, organization, etc., to extract this information. If the entity the user is looking for is not in any of these predefined categories of a named entity recognizer, then crowd workers program their own new named entity recognizer by collecting examples from the web, which acts as a giant corpus of this data. Now, we integrated this workflow into a working system and kind of connected it to the users. So when users ask for a query, a user's query is forwarded to a chatbot that runs on their smartwatch or any voice-enabled device. After which, the query gets forwarded to a WearMail backend through which we recruit crowd workers on demand to A, identify or create a filter set of emails where the information might lie, and B, have the crowd workers write programs to facilitate the extraction. For this, we built a search interface where crowd workers can enter keywords to look at the obfuscated view of their email metadata and interactively select emails. Now, if we take a closer look at the obfuscated metadata interface, first we obfuscate words that are present in the top 10,000 used common words. The intuition behind doing this is that most of the common words are less likely to be sensitive. The way we implemented it was to replace any sensitive text with random characters and then apply a CSS blur effect on top of it. Next, we identify personal identifiers such as names, email addresses, and account numbers with a named entity recognizer and substitute it in all places, including the query. Now, to understand how well crowd workers were able to deal with an obfuscated data, we performed a study. We gathered 24 queries from 6 participants, and for each of these queries, 10 workers selected emails. Then we varied the obfuscation dictionary size gradually to let crowd workers exposing more and more content with a step size starting from 100 words until up to like 10,000 most common words. As you can see in the video, more and more words get exposed as we increase the obfuscation dictionary size. Now, we found that as the dictionary size reached around 1,000 words, crowd workers were able to reach nearly 80 to 100% efficiency in locating the right email. And there was this sort of like linear relationship. Now, after the filter set generation using the obfuscated metadata interface, we looked at how can crowd workers program these named entity recognizers. So as a first step, if the user query involves any predefined data types of a named entity recognizer, such as person, money, or date, then crowd workers simply select the data type in the interface. If the data type is missing, then we ask crowd workers to collect examples from the internet. And in this specific example, a crowd worker is looking for what an ACM membership number would look like. And it turns out a lot of people post this type of information on the internet. We found that not just ACM membership number, but also many data types like Panera bread number, or even High's car rental number, AMC movie ticket numbers, and even sensitive data like social security numbers are shared online. So we utilize this. We utilize the web as a cross-domain corpus where a large number of examples are found, and we construct information instructors on the fly using regular expression, and then we extract that information from a filter set that was generated earlier. Now, more concretely, here's an example. If a user asks a query, what was my Panera bread number? For this specific query, we collected around 20 crowd-generated examples, and it turns out 13 of these examples were incorrect and 7 were correct. So once we collect the example data, we first analyze them for character and white space density, variations in length, and relative character positioning. After that, we discard examples that have a large deviations from the median length. With a few correct examples in the hand, we construct a base regular expression. To account for the variability in examples, we generate a permutations of base regular expression by relaxing and constraining features such as length, sequential character density, most frequent length, and even like ratio of numeric to alphabetic characters. Finally, we have this ranked list of regular expressions in our hand that can, starting from regular expression that can match very specific text to something that can match capture more text. Now we run this regular expression on a crowd-generated filter set to find the matches. As an additional heuristic, we also compute a context rank for each of these matches based on the query keywords that appear before and after the matches. So in this particular example, the keyword order appears 4 times before and after the order number actually appears in the email. So hence its context rank is 4. Finally, we return the top 5 rank list of extracted item numbers to the user. The rank list is generated based on the ratio of context rank and the regex rank. In this particular example, the order number that appears in the top of the list is the correct result. And as you can see, as we go down the list, the results kind of look similar to that, but they're not exactly the correct result. to understand the performance of the email in both filtering and information extraction, we performed the initial evaluation. We invited 5 participants to post around 30 queries on their personal email. The queries closely match categories from our mobile email study. So it consisted of codes like order numbers, security codes, etc., contact information like addresses, room numbers, passport numbers, travel-specific queries like flight confirmation number, and NER queries like money, date, time, etc. So now for our to understand how well the crowd performed in locating the right emails, we took the top 3 voted emails from the crowd and compared it with an automated approach. Our automated approach involved taking the non-stop query keywords and then kind of feeding it through a Gmail search function and extracting the top 3 emails that come out of it. When we look at this graph, the crowd-powered approach performed consistently better than the automated approach. For queries that the crowd were successful in locating the email, we performed the extraction and evaluated how well it worked. Out of the 20 successful extraction, 17 were crowd-generated named entity recognizer, and 3 were the standard named entity recognizer types. We observed that as much as 59% of the time, the successful result appeared in the top of the rank, the first rank, and 35% of the time it appeared in the second rank, and one time it appeared as the fourth result. And finally, the queries that were in the top 5 results were passed on to the user. Of course, our method had its own limitations. First, the users lacked sufficient specificity to help the crowd workers locate the right email. For example, here a user asked, "Where was my meeting last Friday?" And the crowd workers it was not clear to them what this meeting was about and how to locate that. So other kind of like common errors that appeared were, like for example, users oftentimes forgot to abbreviate what keywords they use, like RERC meeting. It was not clear what RERC was. And spelling mistake were more common as well, like DCMA notice number instead of like DMCA notice number. So we think that there can be few recovery strategies. One is crowd workers can kind of interactively ask users to provide them more information to locate the right type of email. For example, more metadata such as from, to, and date could be collected from users, and it could be kind of help them narrow down the right email. So to summarize, WearMail is an interactive crowd-powered system that enables private information search using a privacy-preserving crowd workflow. Specifically, looking at what type of items people were, so we uncovered a mobile email search behavior that specifically looked at what type of items people are looking for on the go. And we introduced like 2 privacy preserving mechanisms. One is looking at how well the crowd workers were able to work with this kind of obfuscated metadata interface. Another is introducing the concept of end user programming with crowd by utilizing web as the cross-domain corpus. Thank you, and I'm open to questions.
I'm curious about some of the Gonzalo Ramos, Microsoft Research. I am curious about some of the obfuscation methods you use. You mentioned you use CSS blurring.
Right.
But that doesn't really cover the data. It's just if I right-click and inspect the web page, I can see the number.
Right. So actually, so what we did was we took the top 10,000 most used common words, and then if the words are not in there, we kind of found them out, and then replaced that kind of sensitive text with some random characters, and then we applied the CSS blur effect.
Perfect, thank you.
No problem.